So these three states can be converted. Yes or no? By rising temperature.
Wait, sir, your screen didn't share again.
Okay, wait,
You share it.
wait. Now it is. Now I'm sharing it.
Yeah, I can see it now, sir.
Okay, now great. So these three states are interconvertible, right?
Yes, sir.
They can be converted by heating the ice. It becomes liquid water, and upon further heating, it can turns to the steam. And if it
Yes,
take out the heat from it by cooling it, the reverse is also possible. Right?
yes, sir.
And this delta sign indicate it is cooling or heating. Plus delta means we are heating it, and minus delta means we are
Yes, sir.
cooling it. We are taking out the heat. Now, the solid becomes liquid, or liquid becomes gases by heating it. And if it take out the heat, the reverse will happen. Getting me?
Right, sir.
So, in different states, matter has some particular force of attraction, right?
Yes, sir.
Different molecules, different substances are different types of interaction. These types of interaction we had done in the grade 11, dipole interaction, hydrogen bonding, London forces,
Yes,
dipole
sir.
radius,
Yes.
right? This we had done in the grade 11. So how strongly they are attracted to each other, that depends upon the types of interaction. So let us discuss this multiple choice question.
Right.
You let me know the answer now.
Yeah. Some space and possesses some mass.
Okay. The second option,
The
correct
option
answer?
B. Yeah. Yeah. Yes.
Right.
Perceivable are three.
Perceivable are
Option
three.
B.
Right.
Yeah.
Good. Which are they?
Solid, liquid, and gas. The
Right.
other two are Bose-Einstein condensate and plasma, which are not
Yeah.
well in real life. So
Right.
that
So
condensate. Yeah. Physical state of matter is the interplay of intermolecular forces.
intermolecular. Good. All good.
Option D. Yeah.
Now, in this chapter, I'm discussing only about one state in detail, that is the solid state. Right. I'm discussing about the characteristics of a solid. Before I start, you tell me what are the possible characteristics of a solid.
Like basic ones, they have a fixed shape.
Yeah.
They have a fixed volume,
Good.
and the molecules only vibrate in their place. They don't move around in a solid.
Mm-hmm.
The uh, what else? They're rigid. No, not always actually.
Yeah, they are rigid. Okay.
Yeah, they're supposed to be rigid at least.
So they have fixed composition, number one, right?
Yeah.
They have a mass, they have volume, they have definite shape, definite density, right?
Right, sir.
Definite shape. And if you compare these three states, packing, can you say it like this? Very close packing in case of solids, very loose packing in case of gases, and some intermediate packing in case of liquids.
Yes, sir.
But I think there is something wrong with the liquid part here. The particles are not separated in the liquid, but their packing is loose. We can like this, we can close, hmm? We can
Oh, okay.
get it. If it had been so, then I should not have a liquid water.
Yeah,
They are
yeah.
bonded with each other. There's something wrong with this type of representation,
Right, sir.
right?
Right, sir.
So very loose packing, least close packing in case of the gases, and very closely packed structure in case of these solids.
Yes.
Density is equal to mass upon volume. You can see I'm fixing the volume, but if you see the mass occupying in it is decreasing. Got it? It means the maximum density in case of the solids, less in case of liquid, least in case of the gases.
Right, sir. Got it, sir.
Now, let us see the microscopic view of a solid. We are looking at a diamond with a microscope. We can see that if we see with more closely, we can see the particles, atoms are packed like this.
Why are they of different colors?
Not,
Diamond is only made of carbon, right?
yeah, but they're only shown different colors. Otherwise, diamond is only one color only made up of one element.
Yes. Right, sir.
Now, I can say the density of the solid is maximum, less in case of liquid and least in case of the gases, right?
Yes, sir.
Exception. I'm talking about the exception case. Density of ice is less than that of water.
Yeah, yeah. That I know. Yes.
Do you know why?
Yeah, due to the anomalous behavior of water, sir. Water has its highest density at 4 degrees Celsius,
Mm-hmm.
after which point it
Mm-hmm.
increases in either direction, sir. So at 4 degrees Celsius, it has its highest density.
Hmm.
In both directions, then it decreases from that point,
All right.
the density. Yeah.
So, can solid be compressed?
No, not.
No,
Yeah, no, it can't be
no. It
compressed.
means we can say the solids are incompressible.
Yes.
Okay.
Yes.
Now, it means solid have strong intermolecular force of attraction. Different
Yes.
type of solid have a different strength of the intermolecular interaction. Right. Some solids have weak intermolecular force attraction, then their low melting point. Some solids have a strong intermolecular force attraction, they have a high melting point.
Yes.
Okay. Are you not, have you noted
Yes.
down?
No, this I understand, sir. This is simply
Okay.
understand.
So these particles seems to be fixed actually. Seems to be, but
Yes.
actually the particles, the atoms, ions are vibrating.
Yes.
Right? We had done in the grade 11 that particle come closer and then again repel and right. They come close
Yeah.
and go away. There's a constant vibration going on in this, whether it is a gas, solid, or liquid, whatever it may be. So they
Your
have
voice is breaking right now.
now. Hello.
Your Uh, yeah, it's a little better now.
Okay.
I'll tell you again, sir, when it's breaking.
Okay. Do you understand the meaning of the vibratory motion now?
Yes, yes, I do.
Right. So what's your answer here?
Fixed. Yeah, all of those.
All of this?
All of these.
Good.
Yes, sir. Solid particles of strong intermolecular forces of attraction, sir.
So option
B, sir. Second one.
yes.
Vibratory motions. So the fourth option, sir.
Vibratory motion. Yeah. Select the false statement.
Solid particles have a random motion. Sorry, they have a fixed position, right?
Yeah.
All solid particles. Yeah, they have fixed positions.
Now let us discuss about the classification of solids. We can classify these as crystalline and amorphous.
Yes.
And now this crystalline solid. Set an example I tell you first. Like we have all the ionic compound, like common salt or any other ionic compound. They are crystalline solid.
Right, sir.
So like common salt, sodium chloride, right? We have two types of ions are there, sodium ion and chloride ion. And how are these
Right.
arranged in three-dimensional space? And if I show you the three-dimensional space, then you can see that after every sodium ion there is a chloride ion, and after every chloride ion there is a sodium ion. There is
Yes,
a
sir.
there is a regular there is a regular arrangement of
Yes.
ions in three-dimensional space. Am I clear?
Right, sir. Yes. Yes, sir. Clear.
So there is a regular, uniform, and homogeneous arrangement.
Right, sir.
Regular, number one, regular. The second is uniform, and it is homogeneous arrangement is
Homogeneous.
observed in the Am I clear?
Sir, your voice cut off a little bit.
Now I don't know
Yeah, it's fine. It's fine now.
because at my end there is all full. It's a good connection. Anyways,
Wait, let me check my side, sir. One second. See if there's any problem here. Yeah, my internet is fast.
then
No problem.
okay. Now I can represent this structure on the 2D like this. After every sodium ion, there is a chlorine,
Right, sir.
right? Like this A,
Yes.
B, A, B, A, B. There is a homogeneous solid. Crystalline solids are
Yeah. Right, sir.
homogeneous solids.
Right, sir.
Now, it exhibit long range order. What is the meaning of the order? Order means some sort of repetition in the structure.
Right.
Some sort of periodicity. Order means some sort of periodicity.
Right.
So, while long range, that simply means continuity throughout the crystal. Continuity throughout the crystal.
Right, sir.
It is like this. Actually, if you look into the crystal structure of sodium chloride, after every sodium ion there is a chlorine. After
So there's six of the opposite ion around every ion. Like there's six chlorine around sodium and
yeah, after
six sodium
yeah,
around
yeah,
chlorine.
yeah. I'm coming to that part also. So by definition, when we say the constituent particles are arranged in definite repeating pattern, that is a crystalline solid.
Right, sir.
Like this. This is the repeating unit, and if you repeat this like and continue like this, I am putting this block one above the another, back and front, and so on. What I'm getting is called as a crystalline solid, and one unit, the starting unit, is called as a unit cell. It means that unit is
Right, sir.
repeated again and again and again, similar pattern, and we get the three-dimensional arrangement packing, and that is got it.
Yes.
And now solve this.
Crystalline solids are homogeneous and have a long range orders. So option A.
Yeah, NaCl is a type of
It's a type of crystalline solids.
yeah. Order implies
Uh, both A and B, sir. Repetitivity and
both A and B. Yeah,
periodicity are
yeah.
both. Yeah.
The basic unit of the crystalline solid is
Unit cells.
yeah unit cell. You got it now. Till now, any doubt?
Yes.
Ask me.
No, sir. No, no.
Okay, right. And now, they have a sharp melting and boiling point.
Yeah.
They have sharp melting and boiling point. What does it mean?
It means all every sample of a pure substance taken melts and boils at the same perfectly sharp temperatures. Like water always, pure water always boils at 100 degrees Celsius and melts at 0 degrees
It
Celsius.
means the complete solid will melt immediately, instantly at a particular temperature. Suppose I say the temperature, the melting point of, let it be of sodium chloride is 700 Kelvin. And I'm raising the temperature
Right.
from 298 Kelvin from the room temperature.
Right,
Right.
sir. Yeah.
So raising the temperature to, let it be 400 Kelvin, nothing will happen. Even a single layer will not melt.
Right, sir.
Right. And rising to 600 Kelvin, even then its temperature will rise, but nothing will happen. You can't imagine that it will melt now. 699 Kelvin, you can't imagine anything, you can't see anything, any change. And instantly, suddenly, at a particular temperature, the whole of the solid melts. And that's the meaning of the sharp melting point.
Right.
Right? And definite heat of fusion means energy required to melt.
For the melting
Yeah.
at the same temperature,
Yeah.
right? Because yeah.
So melting point of water is 0 degrees Celsius. It will melt at 0 degrees Celsius. Before that, it will not melt. Even at -1, nothing will happen. So these solids give a clean cut. They give a clean cut. Means when you're cutting it, we will get the clean cut. Will not get the rough surface. Just like if you cut the wood, wherever you will cut, it will give a rough surface. But if you break the diamond into two part or a sodium chloride into two part, you will get the absolutely plain surface.
Right.
Getting me?
Yeah. Yeah.
So when we try to see through a diamond, how many colors do we see? Many?
Uh, Colors, not
And
sure. I haven't seen as
okay,
many times.
okay. So we see different colors like this. Actually, it is causing the like scattering of light, dispersion of light, basically.
Yeah, yeah.
So in different directions, they have a different color, right? So
Yes,
there,
sir.
so there are many properties which have different values in different directions. Different values in different directions. It means their refractive index is different in different directions. So we say these are anisotropic. Crystalline solids are anisotropic. These are anisotropic. Anisotropic means they have a different magnitude of physical properties in different directions.
So what does that mean exactly?
Okay, I'll tell you how. What is the exact meaning? Just a second. Suppose I say I have a sodium chloride and a positive Cl negative and a positive Cl negative. Got it?
Yes.
If you see any property along this direction, that will be corresponding to sodium chloride, sodium chloride, sodium chloride, right? And if I see any property
Right, sir.
in this direction, the sodium ions will be there. So the property will be different. Magnitude of the property will be different. Yes or no?
Oh,
If I
oh,
see
like
in
that.
this direction, the composition is different. So the magnitude of any property will be different in different directions.
Oh, right, sir.
So that's why I'm saying different compounds, different substances, they have a different magnitude of physical properties in different direction, and this property is called as an anisotropy.
Right, sir.
Physical and property like refractive index, dielectric constant, electrical conductance, all the properties have a different magnitude in different directions. Okay,
Right,
like this. In different directions, there's a different composition, and that is why they have a different magnitude of physical properties.
right,
And now, what do you mean by the isotropy now? You can see that through just a glass, plain glass, you can see that in all the directions, the refractive index is same. And that is why we can't see that here we have different looking different picture, the other different picture, not like that. Or different distortion is there, not like that. We get the same thing. Refractive index is 1.5 throughout. It means there is a something common in everywhere,
right, sir.
right? So refractive index does not change with the direction. If the property does not change with the direction, it is called as a isotropic,
Right, sir.
right? Am I clear?
Yeah. Yes, sir. Clear.
Why do this show? Because the composition does not change with the direction. And this is shown by the amorphous solid, where we have a irregularity in all the directions. Amorphous solids have irregularity in all the directions.
Right, sir.
Getting me?
Yeah.
So, what do you mean by the anisotropy? Different in the physical properties such as dielectrical conductance, refractive index when measured along different directions. I hope it's clear. Hmm?
Yeah. Yes, sir.
And what the reason behind the anisotropy? Because we have a different arrangement
Different. arrangements of particles.
Yeah.
Yeah.
In different directions.
Right. Right.
The type of the crystal that do not show the anisotropy are. Okay, here I have a question.
Right. Not a property of crystalline solids. Wait. They can be isotropic or isotropic, right? So they have a sharp melting point. They have definite heat of fusion, but they can be either isotropic or anisotropic, right?
Mm-hmm.
Which one is it?
They are isotropic in nature. B and T both are correct.
Yeah,
Yeah.
but
Which is okay. They are
they can be both isotropic and anisotropic,
they are
right?
isotropic in nature. They are that is wrong. Yeah. Only D.
Wait, so crystals can't be isotropic.
No, crystal can't be isotropic. Now another property
Oh,
is their sharp melting point. They are anisotropic. They're isomorphous. Isomorphous means two or more substances have same crystal structure.
right, sir.
Like NF, and MgO. Atomic ratio is 1:1, and they have the same crystal structure. Sodium nitrate and calcium carbonate, they have the same type of composition and same type of structure. So these are showing the isomorphous.
Right.
Whereas the crystalline solids are also polymorphous, means a single substance exists in two or more different crystal structures, two different forms.
Right, sir.
Like carbon, right? And graphite, they are the same chemical, but they have a different forms. Monoclinic, rhombic, sulfur exist, graphite, diamond, they're different.
Right. So yeah, allotropy is observed in crystalline forms.
Yeah.
Right.
Like this, rhombic and monoclinic, two forms of sulfur are there. They're polymorphous.
Right.
Multiple choice question. Let us. Crystalline solids are
There, they can be all of these. All of these. Changes with direction. Yeah.
Yeah.
All of the above.
All of these. Good. Understood? Till now,
Yes.
any doubt, ask
Understood.
me.
No, sir. No doubts.
I'm discussing the theory first and then we'll mainly focus on the multiple choice questions. That is your thing.
Yes, sir.
But basically, first we need the crystalline solid we have done. And now I'm discussing about the amorphous solid in detail. Right?
Right. Yeah.
So they have disordered pattern, no regular pattern. They
Right.
show short range order. There's no repetition. They don't have sharp melting point. I'll discuss this point. They don't have sharp melting point. What does it mean? If
Right.
you put a wax and if you find its melting point that is 65 degrees Celsius, right? And now I'm heating it from the 25 degrees Celsius. At 45 it becomes soft. You can compress it. You can, if apply some pressure, you can compress it, right?
Yes.
At 50 degrees Celsius, you can bend it. It becomes so soft you can bend it.
Right.
And after 50 and you come to 55, its upper layer starts melting. And slowly, when it comes to 65,
So it melts uneven, like
yeah,
melts in layers.
yeah, layer by layer. And that is what I say. They don't have a sharp melting point. They exhibit isotropy. Isotropy means similar properties in different directions.
So glass is an amorphous, but glass seems crystalline.
It is amorphous solid. It is
No, because it
technical.
looks regular.
No. Don't look at the. It has a different thing. Internally, we see that it has a different. They don't have a regular pattern.
Right.
On increasing temperature, amorphous solid generally soften and melt over a range of temperature. It means they don't have a sharp melting point. Am I clear?
Yes.
Note it down. Hello.
Yes, sir. I think we got disconnected.
Okay. Can you see my screen?
Yes, sir. I can.
So, do you have any doubt till now?
Yeah. No doubt, sir. No doubt, sir.
So, we have tar, plastic, rubber, glass. All these are amorphous solid.
Right, sir.
Okay.
They are disordered and short range. Yeah, disordered and short range.
Hmm.
Amorphous, all of the above, right, sir?
Hmm.
They all of the above, sir.
Hmm. Okay. Then these crystalline solids are further classified into four types: molecular solid, ionic solid, metallic solid, and covalent solids.
Right, sir.
Now, I'll be discussing these one by one. First of all, I'm discussing about the molecular solids. These are of these three types. Hello, are you there?
Yeah, I'm here, sir.
Yeah.
Just listen.
Non-polar, polar, and hydrogen bonded. I think these terms are clear to you, right?
Yeah, all those terms are clear, sir.
Okay. So atoms like argon, krypton, xenon, these are non-polar, or some molecules may be there which are non-polar, like H2, F2, Br2. These don't have any
Right, but
electronegativity difference, right? So these are
these aren't solids, right?
these are not solid. But at room temperature they are gaseous. But at some lower temperature they are solid,
Right.
right? So among these molecules they have non-polar interactions. They are having non-polar van der Waals force of attraction. They are soft. They don't have any free electrons, so they do not conduct electricity in the solid state. I'm talking about in the solid state.
Right, sir.
Okay.
Yes.
They have low melting point. They are either liquid or gases at room temperature and pressure.
Right, sir.
They're held together by weak dispersing forces or London forces.
Right, sir.
Any doubt in these points?
No, no doubts.
Now, there are some polar molecular solids like HCl, HBr. At certain low temperature, below 0 degrees Celsius, they are solids. At room temperature, gaseous.
There'll be gases, yeah.
But in between the two
Gaseous.
molecules, there is a dipole-dipole interaction. They are also soft. They are also non-conductor. But since interaction is bit more strong as compared to non-polar, so their melting and boiling point will be slightly higher.
Yes.
Most of the gases are gases. Most of these are gases or liquid at room temperature.
Right, sir.
They are held together by strong dipole-dipole interaction.
Right, sir.
Am I clear?
Yes.
Next is the hydrogen bonded. You know that those compounds where we have
Yeah.
a hydrogen bonding, like water in the ice, they are also non-conductor of electricity.
Right, sir.
Any doubt till now?
No doubt, sir.
Now, it means now we can compare that in case of the non-polar particles, we have this dispersion forces. And what are the dispersion forces that I have already discussed in the grade 11? Temporarily, the electrons are revolving and they come to the one side. It become
Yeah.
polar. It become polar,
Yes, sir.
right?
Yeah, that's what
And
London forces.
and then it induces the polarity on the other,
Yes, sir.
right? Distorted, and then interaction between two particles take place, and this is known as a London forces, right?
Yes, sir.
In case of the polar particles, we have a dipole-dipole interaction.
Right, sir.
You know that dipole-dipole due to difference in electronegativity.
That's a hydrogen bond.
Yeah, hydrogen bond.
What they showed before.
They should have written here the HCl. HCl would have been
Yeah.
better example.
HCl would have been dipole. Yeah.
Yeah, and get the hydrogen bonded. You know, the hydrogen must be bonded with the F or N, right?
Right, sir.
So these are the constant particle and what type of interactions are there. Like we have hydrogen, chlorine, neon, carbon monoxide. They're all non-polar molecules. Sulfur dioxide, HCl, they're polar molecule. So here we can give examples, right?
Right, sir.
Any doubt till now?
No doubt, sir.
Now, among the interaction in the non-polar, we have a London forces
Yeah.
or dispersion
Right, sir.
forces. In case of polar molecule, what type of forces are there?
There's the dipole interactions.
Yeah. In case of hydrogen bonding, we have hydrogen bonding, right?
Hydrogen bonds. Yeah.
At room temperature, they are the non-polar gases. Polar are also gases. Hydrogen bonded are volatile liquids.
Yeah. Right, sir.
This is at the room temperature, right? But if I talk about nature of the solid, they're soft, soft, soft. All are soft.
Right.
Melting point lowest in case of the non-polar. greater than non-polar, and greater than polar. Stronger the interaction, more the melting point.
Right.
Conductivity, non-polar, non-polar, and non-polar. All these are non-polar. All these are non-polar.
Right.
Getting me?
Yeah. Got it, sir.
Now, which is not a type of the crystalline solid?
Uh, Non-metallic solid. There's no
Yeah,
such thing.
good, good.
Yeah.
Order of melting point.
Okay. Yeah. Order non-polar, then polar, then hydrogen bonded.
Opposite you are talking about. Huh? I'm talking about decreasing order.
Right.
Inert gases are held together by
Held together by London forces mostly. Yeah.
and
London and dispersion forces.
force.
Yeah. Sorry.
Yeah, both of these.
London and dispersion.
What is water example of?
What is an example of hydrogen bonded?
Yeah,
Yeah. Molecular. Yeah.
got this in all this till
Yes.
now.
Got it, sir. Got it.
And not, till now I have discussed the molecular solid. Now I can discuss about the ionic solids.
Right, sir.
Ionic solids. What are ions? Positively charged. Anions are negatively charged.
Yeah.
And these two
Yeah.
charges, if they're attracting with each other, the electrostatic attraction will be there.
Yes, sir.
Right.
Right, sir.
And the ions are bonded with each other by the electrostatic force attraction. I have shown this sodium chloride in 2D and 3D.
Yes, sir. You are.
In 3D, every cation, means sodium ion, is surrounded by 6 anion, 6 chloride,
Yes, sir.
and every chloride ion is surrounded by 6 sodium ion. Right. There's a definite regular geometry. I can say that these are the crystalline solid.
Right, sir.
Right. So the interaction between the two opposite charges will be attractive, and between the
Right,
two
sir.
similar charges it will be repulsive. Right.
Yes, correct.
Since they are charged particles, so the total charge should be neutral, right? It means the number of the positive ions should be equal to number of negative ions. Yes or no?
Yes, sir. Yes, sir.
So the total charges in ionic solid are well balanced, hence they are electrically neutral.
Yes.
Right?
Yeah.
So anion is surrounded by the cation and cation is surrounded by the anion. And this arrangement, how they will be arranging themselves in three-dimensional space, that depend upon three factors: size of the ion, charge on the ion, and extent of polarization.
With so, sir, it won't always be 6 around each.
In different compound, the different arrangement will be there. Not necessarily always 6.
Oh, so it won't always be a cube-like structure.
Not necessary.
Okay. Right, sir.
Right.